Any receiver, whether it be a television or broadcast set, a military radio or radar receiving set, must be tuned accurately to the same frequency as the transmitter to allow reception of the signal. Weather changes, such as cold, heat, or dampness, jarring or vibrations, variations in tubes, and other factors affect the tuned circuits in all radio receivers, causing loss of sensitivity, selectivity, or ability to separate stations or frequencies, or loss in signal strength.
Reduced with limited attacks and probing accuracy as peace talks progress. As Admiral John cited the peace talks, the UN and Communist subcommittees near agreement on the location of the ceasefire line. A deadlock exists over control of Kaesong's original location of the truce talks.
The tuned circuits of any receiver must be accurately aligned to operate at maximum efficiency to permit reception of each of the transmitting stations or frequency channels. To test or realign a receiver, signals are needed on several frequencies in order to accurately adjust the circuits of the set. So, the signal generator or oscillator is used. The signal generator may be defined as a miniature transmitter, producing a signal of any desired frequency and strength to test radio and other electronic equipment. Signal generators employ high voltages, often enough to endanger life if they are not used properly. Signal generators take many forms. Some are designed for generating audible or audio frequencies only. One type provides both radio and audio frequencies. This one is for use with FM receivers. This one is for use on radar or similar equipment. Others are capable of generating a signal on only one or two specific frequencies. However, most signal generators used in communication work operate on the same basic principle. High-frequency AC power produces the signal. A vacuum tube in a suitable circuit may be made to oscillate and generate high-frequency AC power. An oscillator is simply a vacuum tube amplifier with the output coupled to the input in order to generate or sustain oscillations at the frequency desired. There are numerous oscillator circuits, of which this regenerative circuit is one example. Part of the voltage developed in the output circuit is fed back by transformer action to the grid or input circuit. The reinforced grid voltage is amplified by the vacuum tube, increasing the plate voltage, and then is again transferred to the grid circuit. This process is repeated as long as power is applied. The frequency is determined by the values of the coil and condenser circuit and may be varied over a specific range by varying the capacity. This and other oscillator circuits, using various coupling methods to develop feedback, are called self-excited oscillators. In addition to the fundamental frequency generated by an oscillator, it may also produce several frequencies which are multiples of the fundamental, although weaker. For example, if the tuned frequency is 1,000 kilocycles, a weaker signal may be generated on 2,000 kilocycles, 3,000 kilocycles, and so on. Some signal generators utilize these harmonic frequencies to extend the range of the generator. Another oscillator is the crystal-controlled type, designed to operate on one or more specific frequencies and is not variable. The important thing in the crystal-controlled oscillator is quartz. Quartz when cut and ground to accurate dimensions and placed in electrical field, will vibrate at a particular frequency determined by its physical dimensions. The mounted crystal for the indicated frequency looks like this. This is a simple crystal-controlled oscillator circuit. The voltage required to start the crystal vibrating is transferred from the plate of the tube to the grid and then to the crystal. The resulting vibration of the crystal develops a voltage which is applied to the grid and amplified by the tube. Then some of the voltage returns from the plate to the grid as before. This cycle continues, and we have oscillation. This circuit will generate a voltage on one specific frequency, known as its fundamental frequency, and the oscillator will produce harmonics, or multiples of the fundamental frequency, but it cannot cover a continuous band of frequencies. For example, if the fundamental frequency is 1,000 kilocycles, it will emit weaker signals on 2,000 kilocycles and 3,000 kilocycles, but it will not transmit a signal on any frequencies in between. By the addition of one or more crystals and a switching system, signals may be generated on other specific frequencies. This signal generator furnishes a signal on two frequencies. Note the two crystals. The audio oscillator, or signal generator, provides signals in the audible range. This is a typical unit. The audio oscillator is connected to an amplifier and loudspeaker. This produces a signal in the loudspeaker that sounds like this, as it is adjusted through its frequency range. Frequencies audible to the human ear range from about 20 cycles per second to a maximum of 20,000 cycles per second. Note the change in the tone of several different frequencies. In a great many audio frequency tests, a variable frequency oscillator is not essential. Because one audio frequency is usually sufficient for the necessary tests, most radio frequency signal generators include one audio frequency, normally 400 cycles. This makes the use of separate audio signal generators unnecessary, except for highly specialized work. A number of signal generators are required for the different ranges used by the various types of signal equipment. This signal generator is designed to operate on the ultra-high frequencies, covering a range from 2,700 to 2,900 megacycles, and is used in radar work. This one is designed to align, test, and calibrate frequency modulation radio receivers. This unit goes from 100 to 32,000 kilocycles. It is a general-purpose, amplitude-modulated oscillator covering a wide range of frequencies used in radio work. Let's examine the how and why of its operation. It has its own power supply with vacuum tube rectifier for producing DC voltage from a 110-volt AC power source. It has a filter system. And, of course, a vacuum tube oscillator. So far, we have an oscillator plus a power supply. Next, for an explanation of modulation. Note the output switch. It is marked modulated, unmodulated, and 400 cycles. Radio frequencies, being above audible range, cannot be heard. To make it possible to hear our RF signal, it must be modulated with an audio signal. Now back to the tickler oscillator circuit. Suppose it is producing a radio frequency signal, which looks like this. To modulate it, a transformer is placed in the grid circuit with the input side of the transformer connected to an audio oscillator. The audio signal has fewer alternations per second and has this form. When the audio signal is impressed on the radio signal through the transformer, the resulting amplitude-modulated signal has a waveform of this shape. This signal will produce an audible output in a receiver. Now we have a modulator added to the circuit. Thus, when the output switch is on unmodulated, the result is the normal RF wave as produced by the oscillator. If the audio signal only is desired, switch to 400 cycles, which in this generator is the frequency of the modulator. Much testing of audio circuits is possible with an audio signal of a single frequency. With the switch turned to modulated, the audio signal is superimposed upon the RF signal so that the RF signal's amplitude or height is varied to correspond to the shape of the audio signal. The oscillator is now said to be amplitude modulated. The next step is adjusting the equipment to the desired frequency. This is done by first setting the band selector switch to the band required. The switch places different coil and capacitor combinations in the oscillator circuit, each covering a portion of the frequency range. Then tune to the exact frequency by varying the main oscillator tuning capacitor. But before connecting the signal generator to the equipment to be tested, the strength of its output must first be controlled. The controls used for this purpose might be compared with the volume control of a radio receiver, only here transmitted energy is being controlled. These controls are called attenuators. One is for fine control, the other for broad control. In preparing the signal generator for operation, the attenuators should always be turned to the position of minimum output, since a low rather than high output is desirable in most testing operations. And so the attenuator is added to the circuit system. Now returning to the radio receiver, before it can be aligned, it must be checked thoroughly to eliminate all other defects. Tubes are checked, voltage tests made, and a careful visual inspection accomplished. Aligning a set that has other defects only means repeating the whole process again, since change in the constants of the set, such as a new tube or capacitor, affects the alignment. So repair first, align last. If a receiver is not normal after all other defects have been eliminated, it probably needs alignment. This is particularly true if the receiver shows any of these symptoms: weak signal strength, lack of selectivity, or incorrect tracking. That is, the frequency marking on the tuning dial is a great deal different from the frequency of the transmitted signal. Now, with some understanding of how a signal is generated, Let us put it to use and test the radio receiver. A signal generator is not connected directly to the equipment to be tested. If a radio receiver is to be tested for sensitivity, a phantom or dummy antenna is connected between the signal generator and the receiver. The phantom antenna simulates a real antenna in that it roughly duplicates the electrical properties of the real antenna. If a phantom antenna is not available, a small capacitor may be used. It is connected in series with the signal generator. A capacitor must always be used when attaching the signal generator to a point where DC voltage is present. This will prevent the DC voltage from entering and possibly damaging the signal generator. Thus, the phantom antenna, or capacitor, takes its place in the system and is attached to the equipment under test. Now there is the source of the signal established and the set to receive it. The receiver is tuned to the same frequency as the signal generator. But an indicating device is needed to show the amount of output that is going through the receiver. By using a modulated signal, the signal can be heard on the loudspeaker of the set. But for close adjustment of the receiver, a more accurate indicator than the human ear is needed. An AC meter of the copper oxide rectifier type is an accurate indicator. It may be calibrated in decibels, the unit of sound power, or it may simply be calibrated in AC volts. With the addition of the meter or indicating device connected to the output of the radio receiver or other equipment under test, the circuit is complete. Don't overlook the tech manual. Alignment procedure, connections, and frequencies vary with every type of equipment, so that no set can be aligned without knowing every detail of the operation. Complying with the instruction for this set, we start with the intermediate frequency amplifiers. The correct intermediate frequency for this particular receiver is 465 kilocycles. We now set the signal generator to this frequency. Then we must connect the signal generator to the input of the first IF stage, since the IF frequency will not pass through the RF amplifier. The IF transformers are adjusted to maximum output indication on the meter. The signal generator output is reduced to prevent overloading the set. The goal here is not an exact meter reading, but the point of maximum deflection. The adjustment screw is always turned past the point of maximum deflection, then back and forth 2 or 3 times. The oscillator and RF circuits are aligned in a similar manner, but on different frequencies. For certain types of work, particularly that involving waveforms, the cathode ray oscilloscope is used in place of the output meter. Here, the signal generator frequency is varied at a certain rate over a band that extends 5 kilocycles on either side of the IF frequency. The oscilloscope sweep circuit is synchronized with the signal generator frequency sweep and produces a curve which is a reproduction of the selectivity curve of the amplifier under test. This is very helpful in tuning the IF amplifiers to pass a certain band of frequencies and exclude all others. A different type of signal generator is used in the alignment of frequency modulation receivers. Usually, a special frequency modulation signal generator, such as this, is used. The basic principles, however, remain the same. Again, specific operations vary with each set, so it is necessary to refer to service data of the set concerned. Another important use of the signal generator is in signal tracing. Receiver troubles can be localized by connecting a signal generator to the antenna terminals of the receiver and feeding a modulated signal to the set. The stage in which the fault occurs can be determined. An indicating device, usually a vacuum tube voltmeter, is connected to the input, then to the output of each succeeding stage. When the signal disappears, the defective stage has been located. The frequency meter or wave meter is not used as other signal generators, but it is closely allied. It is a precision instrument, and a calibration chart is included with each set to ensure accuracy in tuning. This set is used for the generation and measurement of radio frequency signals to an extremely accurate degree. It serves also as a radio frequency standard in the tuning and calibration of radio transmitters and receivers and signal generators. The frequency meter might be called a signal generator to test signal generators. The signal generator, through jarring or other mishap, may get out of alignment. A frequent check of the calibration of the signal generator with the frequency meter is advisable. It is only a matter of sending out a signal on the generator, which is received by the meter. The frequency meter is tuned to the exact frequency until a zero beat is reached. If the meter and generator dial readings agree, the generator is in tune. A tolerance of 1 or 2% is allowable on most signal generators. Of course, this procedure must be accomplished on each band to check the accuracy of the entire range. Remember, these are fine precision instruments. Dropped or mishandled, their immediate value is at an end. And now, what's most important to remember about the signal generator? It is a miniature transmitting set used to transmit signals of various frequencies at different levels of power for the purpose of testing and aligning electronic equipment. It is composed of an oscillator to produce AC power at radio frequencies, and a modulator circuit which superimposes an audio signal on the radio frequency signal. There are many types of signal generators, but they all perform the same basic job. Signal generators must be used in accordance with instructions contained in the technical manual pertaining to the equipment to be tested, as procedure differs with each piece of equipment. They must be used in conjunction with an indicating device. First, the signal generator transmits a signal. Then the equipment under test receives it. The meter or oscilloscope indicates the result. Take the trouble to learn how to use it properly, taking care not to damage it, and the signal generator will soon be helping to keep your communication equipment at top efficiency, making your job seem less like work.